Optical character recognition on encoded video data for embedded systems by Chem2, Team Embedded Vision 2. My name is Hojung, and our team has been working on text detecting and recognizing neural network model targeted for embedded devices. Before I go into details of our work, I will explain key background knowledge. Optical character recognition, short for OCR, detects and recognizes text and words from images. When it comes to designing end-to-end solution for OCR, the neural network's task is usually divided into two: text detection and text recognition, where text detection locates areas in the image where texts are found, and text recognition scans those proposed areas and recognizes words. One popular example would be the scanner feature of Google Translate app, where the app translates words into language of your choice on the fly. Next, we'll talk about embedded systems. It is a system with bare minimum parts to allow computing power. So it has parts like computer processor and computer memory. On the left, we can see an example of how an embedded system looks like. They're powerful because they're sort of generalized version of computers and more lightweight. As a result, they're mostly used on top of existing devices, and specifically, they're embedded on top of devices like industrial robots, GPS receivers, and so on to make these devices smarter and more powerful. Our goal is to develop an efficient solution that detects and recognizes text from day-to-day scenes that is to be deployed on embedded devices such as Raspberry Pi. Detecting and recognizing words from images has become a somewhat mature technology. For example, car plate recognition used in crime purposes or public parking systems are quite used in practice. However, the ability to utilize the technology on embedded devices is quite challenging due to relatively lower computational ability, and it makes the study non-trivial. Let's look at how our solution is implemented. Following from the diagram on the right, we have a video file as an input. Our first block is sampling block, which is used to selectively pick frames from video files. These retrieved frames are then passed to detection block. As briefly mentioned before, detection block proposes target areas where words reside. These proposed areas are then passed as coordinates to our next block, which is the recognition block, where the neural network model figures out what the characters in the proposed areas of images are. Then lastly, we test our model with question text files. Let's take a closer look at each of the blocks. Our first block is video sampling block. Traditionally, when analyzing video data, video frames are decoded from their compressed format and then inferenced upon. Because many frames contain overlapping information, and some frames are low quality due to motion blur and lack of objects, this traditional method leads to a large amount of wasted computation time. In certain settings, such as on embedded devices, computational efficiency is very important. An encoded H.264 video consists of I frames, P frames, and B frames. I frames have their full pixel data stored, while P and B frames have only what is known as their motion vector data stored. Typically, P and B frames are divided into 16 by 16 macro blocks during video compression. The displacement of each macro block in these frames relative to their reference frame is their motion vector. By analyzing motion vectors of encoded video data, we can understand whether a frame is in high motion or not. Frames experiencing a high amount of motion are unlikely to contain data that will be understood by our neural network. Using this knowledge, we can implement a solution that only inferences on low motion frames. In addition, because objects are not likely to change more than once per second, we can choose to extract only iframes from encoded data. In .mp4 files, there's one iframe every second. This allows us to extract 1 frame in every second of video data without any need for decoding motion vectors. Next is our EAST detector block, short for Efficient and Accurate Syntax Detector. EAST uses a fully convolutional neural network and non-maximum suppression merging to detect text in an input image by encasing the prediction in bounding boxes. EAST detector has a few advantages compared to other text detectors. Unlike others, EAST does not require extra intermediate computation like candidate proposal, text region formation, and word partition to detect text in images. It can handle low-resolution images, non-uniform illumination, and varying orientation. Lastly, it shows high stability on videos with various forms of text instances. The main challenge faced when implementing EAST was reducing the amount of computation to decrease runtime and improving accuracy of text detected. This was challenging because these two characteristics are usually inversely proportional. To decrease the runtime of EAST, a small lightweight feature extraction network, PVA-Net, was incorporated. Next is our text recognition block, which is Connectionist Temporal Classification, short for CTC. The purpose of CTC is to translate a picture of text into a computer string. To do this, CTC first uses a convolutional neural network to extract features from a picture of text and divide the features into a number of evenly spaced columns as shown in the output of CNN in the picture. After that, each column of feature will be forwarded into a recurrent neural network to predict one character per feature column. Lastly, the CTC decoding will be used to construct the final string. Ideally, each feature column will contain exactly one character, and all we need to do is to combine all the predicted characters together. However, that is a huge assumption and does not reflect reality, as some feature columns will have no characters and some characters might stretch across multiple columns. To solve that, we'll look closer at how CTC decoding works. To solve the problem that some column features might not contain any characters at all, we introduced a blank class denoted by the epsilon sign in the picture. To handle the problem that some characters might stretch across multiple column features, the first step in the decoding process is to merge repeated characters. After that, the blank class is removed and the remaining characters are concatenated together to form the final output. This decoding scheme increases the robustness of CTC to handle words of all sizes and styles. The main challenge faced when training the CTC model is the dataset imbalance from the ICDAR 2015 dataset. Roughly 5% of the dataset contains the word sale, and that is a big problem as the model will favor the word sale over others. Since the machine learning model's main aim is to simply increase the accuracy, the model learned to predict sale all the time and settle with the 5% accuracy. This is undesirable, as what we want is for the model to handle all kinds of inputs. To solve the class imbalanced issue, a huge synthetic dataset of 7 million words was incorporated. Shown in the picture is how the synthetic dataset is generated. With such a huge dataset, the class imbalanced issue is solved because now the word sale makes up only a tiny part of the entire dataset, and the model is forced to learn to handle all kinds of inputs. After training for days, the model performed well and only messed up a letter or two per prediction. Shown in the picture is some of the CTC model's predictions. The top row is the model's prediction and the bottom row is the ground truth. The model managed to achieve a validation accuracy of roughly 95%. Here are the initial experiment results. Our team is still working on the solution and we hope to update the result as soon as we can.